The next capital budgeting technique we want to discuss is the internal rate of return, or IRR. IRR is the discount rate that forces the present value of all the cash inflows equal to the cost. So this is the same as forcing NPV to be zero. To explain this, we look at NPV versus IRR. To calculate NPV, remember we enter a discount rate and we calculate the total present value. The result is the NPV. Now for IRR, we want this NPV to be zero and solve for this discount rate that makes the NPV zero, and this discount rate is the IRR result we are looking for. So if we look at this timeline for project L, what is this project L's IRR? To solve for this IRR, we know the cash outflow, or say the cost, is 100. And if we calculate present value of the first year, present value of the second year, and the present value of the third year, these three present values together should equal to 100. Or say these three present value plus a negative 100 should be 0. That's why we have a 0 NPV. Now remember, PV1 is 10 divided by 1 plus a discount rate, and PV2 is 60 divided by 1 plus a discount rate at the power of 12, right? So we're looking for that discount rate that give us PV1, PV2, and PV3, so that all together they can match the 100. Mathematically, it is hard to solve for the IRR by this formula, but with your financial calculator, it can be easy. We just need to enter the cash flows. Negative 100 is the CFO. The first cash flow is 10, second cash flow is 60, and next cash flow is 80. So the inputs of the cash flows are pretty much the same as the inputs you use to calculate the NPV. But instead of entering the discount rate and calculate NPV, now after entering cash flows, we simply try to compute IRR and get the IRR results. The result turns out to be 18.13%. And again, if you want to try with your financial calculator, and you can refer to the video I posted on D2L that show you how to use a financial calculator, including how to calculate the IRR with your financial calculator. Now, as a practice, for project S, and if you follow the same approach, you can compute for the IRR, and it turns out to be 23.56%. So what's the rationale for the IRR method? We say IRR is the project's rate of return, and the WACC is the project's cost. So for example, if a project requires 100 million capital investment, then every year if we calculate IRR, IRR is the rate of return out of that investment. And WACC measures the cost of that capital that you raised. So we want IRR to be greater than WACC, or say we want the rate of return to be greater than its cost of capital. If that's the case, then some return is left to boost shareholders' wealth or shareholders' returns. So in our example, for project L, IRR is about 15% and WACC is 10%. Remember, we used 10% to calculate the NPV of the project. So if you have IRR greater than the WACC, then project L is adding extra return to the shareholders, and that is a good project. Now let's talk about NPV profiles. If we enter the cash flows into our calculator to find NPV for project L and NPV for project S at different discount rates, we can come up with the following results. For example, when WACC is 10%, then for project L, the NPV is about 19, and for project S, the NPV is about 20. If WACC is 15%, or say if we use 15% as a discount rate, then NPV for L is about 7, and NPV for projects is about 12. The results can be presented in the graph on the next slides, while the horizontal line captures different level of the WACC, and the vertical line captures different NPV results. So we have this red curve for project L, and the yellow curve for project S. And as you see, for both projects, the so-called NPV profile curve goes downwards, meaning that higher WACC, or say higher cost of capital, then lower NPV from the projects. For each project, if you look at where the NPV curve meets the x-axis, or it meets the horizontal line, this is the IRR. This is the discount rate that makes NPV 0, and that's the definition of IRR. So IRR for project L is here, which is about 18%, and IRR for project S, that's where the yellow curve hits the x-axis, and that's about 20.6% IRR for project S. And as you see, these two curves intersect at this one point. Well, they have the same level of NPV, and that's when the discount rate is about 8%. So if we are looking at just one project or several independent projects, remember for independent projects, you just have to look at the projects one by one independently, right? So in that case, NPV and IRR can lead to consistent decisions, which means when NPV is greater than 0, IRR will be greater than the cost of capital, and that's when you want to accept the project. And when NPV is less than, or say lower than 0, and that's when the return IRR lower than the cost of capital, and in that case, either way, you want to reject the project. However, when we look at mutually exclusive projects, NPV criteria and IRR criteria can lead to conflicting conclusions. Remember, for IRR of project L is here, and IRR for project S is here. So there's no doubt that IRR for project S is greater than the IRR of project L, which seems to suggest that project S is always better than project L. But if we look at NPV, we may have different story. For example, if WACC is 5%, which is 5% here, lower than the 8.7%. 8.7% would be what we call as a crossover point, while project L and project S have the same NPV. Now when we have a low WACC and apply the low WACC, say 5%, to both project L and project S, we understand that project L's NPV is here and project's NPV is here, which means project L has a higher NPV than project S when WACC is about 5%. If we follow the NPV rule, then we would choose project L. But then if we look at IRR, project S has a higher IRR. So that presents a conflict. Which one do we choose, S or L? Do we follow the IRR rule, or do we follow the NPV rule? We say NPV and IRR actually are based on different reinvestment rate assumptions. NPV assumes that future cash flows are reinvested at the WACC, which is the opportunity cost of capital. IRR actually assumes that future cash flows are reinvested at IRR. Generally, reinvesting at opportunity cost, the WACC, is more realistic, so NPV method is usually considered to be more reasonable, and then NPV should be used to choose the two mutually exclusive projects. So we can reach a conclusion here that we should choose the project with higher NPV, and which project would have the higher NPV also depends on what level of WACC we are using. Remember, we just mentioned that IRR is based on the assumption that cash flows are reinvested at IRR, which sometimes is not that realistic. So we can modify this IRR and calculate a modified IRR, which assumes that cash flows are reinvested at WACC. The definition of MIR is that it is a discount rate which causes the present value of a project's terminal value to equal the present value of cost. This so-called terminal value is calculated by compounding inflows at WACC, or say assuming these cash inflows are reinvested at WACC. If this sounds a little bit complicated to you, we'll explain this calculation for project L on the next slides. Look at the timeline for project L. Initial cost 100, and that is the present value, and that is also the present value of cash outflows. We do have cash inflows at year 1, year 2, and year 3. Now we assume these cash flows will be reinvested at the WACC 10%. $10 reinvested at 10% for 2 years, that's why we have 12.1. And 60 reinvested at 10% for 1 year, that's why we have 66. And the 80 to be received at the end of year 3 would have no time to be reinvested, so it's 80 itself. And we sum up these 3 numbers and we get a total of 158.1 by the end of year 3. And that is the total terminal value of all the inflows, assuming that they are reinvested at the cost of capital of 10%. So then the question is, if you have an investment of $100 and it becomes 158.1 at the end of year 3, no matter what happens during these 3 years, if you compare these 2 numbers, what is your return every year so that your 100 investment becomes 158.1 in 3 years? And that is a simple time value of money calculation. So if we try to find this discount rate, and this discount rate is the modified IRR we are looking for, and you can use 158.1 divided by 100 and get the third root of it, and then minus 1, you get 16.5%. And of course, you can use your financial calculator or Excel to solve for this discount rate, and either way, you should get 16.5%. To summarize the MIRR calculation, step 1, you should find all the future values of all cash inflows. You don't necessarily have to follow the steps here. You can just simply calculate the future value of every cash inflow and then sum them up. You get 158.1 in our example. And for step 2, you find the present value of the cash outflows. In our case, it's simple. It's just $100 at time 0, so it's 100. And then you find the IY, the interest rate, or say the discount rate between the total future value, or say the terminal value of all the cash inflows, and the present value of cash outflows. So it is between 100 and 158.1, and you're trying to find this IY. What I have here, this is to use the financial calculator, but you do not have to do it this way. And you can follow either the formula or you can also use Excel. Either way, you should get 16.5% modified IRR.